All right, hello everyone. Welcome to another CU Prime Talk. So my name is Tyler, if you don't know me, and this is a CU Prime Talk. So what is CU Prime, you might ask? Hopefully you all know. If you don't, CU Prime is a student organization in the physics department that is devoted to promoting diversity, equity, and inclusion. And we do that a number of ways. One of those is by hosting this talk series. And so we have grad students come in each week, or students who do research, and give talks about their research, what grad school life is like, and so on and so forth. So for everyone in the room, we have plenty of pizza. Be sure to sign in either on the laptop, or you can scan in that QR code over there. And if you're joining on YouTube, then welcome. So if you have any questions at any point, feel free to interrupt. We'll have some discussion questions throughout where you get a chance to talk to your neighbors. And otherwise, we'll go ahead and get started. So our speaker today is Iona Binnie. She is a graduate student who is going to tell us all about skyrmions. And she'll explain what those are. They're really cool things. And she is also an instructor for the CU Prime class, which is running each fall semester. And so you guys probably already know her pretty well if you're in that class. All right, so without further ado, let's give it up to Iona.
All right, so as Tyler said, I'm Iona. Before I get started, I want to tell you just a little bit about my group. So I work in the Captain Mernan group. And while a lot of groups in physics research are kind of brought together by studying one particular thing, my group is more brought together by the tools we use to study many different things. And the tools we use fall under this umbrella of coherent ultrafast X-ray science. That probably is not going to make sense right now, but what I'm going to do in this talk is zoom in on one of these particular applications and tell you how these tools help me study that. So the outline, I'm going to tell you first about what particular application I study, and then how ultrafast and ultraviolet tools make this possible. I'll go into a little bit of detail about the experiments, and then finally I'll talk a little bit about my journey through physics as part of the CU Prime initiative. So first of all, what do I study? Skyrmions. How many of you have heard of skyrmions? Raise your hand if you've heard of them. Not very many. I'm not surprised. And this picture is probably not very illuminating. The term comes from this guy, Tony Skyrmy. He was a theoretician. But I'm going to try to explain what these things are. So to understand what a skyrmion is, we need to start with the magnetic field in a material. So the magnetic field in a magnet, you can think of it as, you zoom in to the individual atoms, each of them has their own tiny little magnetic field. We can call that a magnetic moment. And those all add up together to create the magnetic field of that material. So if they're all aligned in the same direction, that can create a stronger external magnetic field that we could measure outside of the material. So if that makes sense, the next step is I want you to imagine that we have a row of these magnetic moments. And I'm going to represent that with this rope ladder that's connected by two ropes on either side. And the reason I'm using that analogy is because the magnetic field of each of these moments exerts a force on each other moment that kind of makes them tend to want to align, rather like the rope ladder. You know, if the ropes are stretched tight, if I were to pull on one, the other ones would kind of want to pull to be next to it as well. So they want to be pointing in the same direction. So this system is pretty simple. Now imagine that I took the ends of this rope ladder and detached them and gave them a full 360-degree twist and reattached them. The bars of the rope ladder would all rearrange to do a full circle, kind of like this twist down here. I'm doing the same thing with the ladder as I'm doing with my magnetic field. So now you can imagine if I were to try to twist these no longer line up perfectly next to each other, right? There's a small twist between each one. I could go along the ladder and try to make them all stand up straight next to each other. But by the time I got to the other end, I'd have a twist in the rope That'd be causing a lot of tension. It would be very difficult to twist all the way. So that full twist provides what we call topological protection. This full twist is stable. It's hard to unwind. If I just tried to do a partial twist, then it would kind of go back to being all aligned in the same direction because of that restoring force that makes the bars of the rope ladder want to point in the same direction. This protection is fundamental to what makes a skyrmion. A skyrmion has this kind of protection, stopping it from wanting to unwind. You can extend this twist idea into higher dimensions. If I take that twist and rotate it around in a circle, I might get something like this. If I translate that to a three-dimensional sphere, you might get something like this hedgehog structure. Maybe you can see why that would be called hedgehog. And these are a little bit hard to visualize, but the thing that connects all of this 1D, 2D, and 3D protection is that if I took any one of these arrows and I slowly went around and tried to make all of the arrows adjacent to it point in the same direction, eventually I would get to two arrows that are completely anti-aligned. And that is not, I'm going to personify my magnetic moments. They don't like it. It's not energetically favorable. So that is kind of what characterizes skyrmions. What makes these useful? Why would we want to study them? So as I already said, they're stable and long lasting. That can mean on the order of hours or even days. And you can make them stable at room temperatures. You don't need like a cryogenic freezer. And you also don't necessarily need to be applying some really strong magnet to your skyrmion material in order for these to persist. It's also possible to move them around. You can kind of propagate the disturbance in the magnetic field. And they also have these separate distinguishable states. For example, you can have one winding in a clockwise direction and another winding in a counterclockwise direction. But what makes these properties useful? I'd actually like you to discuss that with your neighbor. Think about these properties that some material might have. What makes these useful? I'm going to give you 3 to 5 minutes to discuss. Turn to your neighbor, introduce yourself, talk about what you think. Go. Does anyone want to share their answers? I have a volunteer to share an idea of what makes these things useful. Yeah.
I guess it's just really useful for observations because like you don't have to like situations just at room temperature. You just can study it for a long time instead of like 50 seconds or something.
Right. Easier to do experiments on them. That is a great point. Yeah.
This is a little bit of a wild idea, but maybe for data storage.
For data storage, that's not such a wild idea. That's kind of what I'm getting at. Any other ideas? Yeah. For quantum computing, I've seen a talk about that. I mean, specifically using skyrmions. So yeah, these you guys got right at the ideas. Those are the qualities of something that might be useful for data storage and even for logic if you can move them around. I saw a talk on using skyrmions for quantum computing, but I would need to see it again to make sure that I really understood it. So this is why we want to study them, possibly to apply them in future magnetic-based technologies. And there's actually all kinds of weird things beyond skyrmions. You can imagine doing multiple twists or like twisting in one direction and twisting in another direction. I'd love to study some more of these weird skyrmions. But this has all been very abstract. I'm just kind of showing you maps of little arrows. I want to take it back to something more concrete so you can imagine what this looks like when we have it in the lab. Oops, skip a slide. So the arrows represent, remember, the magnetic moments of the atoms in a material. That material, in my experiment, is this tiny little thin film of metal. If you were to zoom into that film, you would see layers of iron and gadolinium. This is not a picture of my sample. This is a cake.
Okay, I was ready. That rest don't make sense.
So it's a little tiny piece of metal that has these multi-layers. And if you could see the skyrmions in that sample, they would look like little tubes that run through the thin layer. The tubes are around 200 nanometers across, and they kind of arrange in this hexagonal pattern. So that's just to, when I talk about skyrmions, I have this very abstract picture in my head, but I also have a tiny little square of metal that I need to keep safe in the lab. So if we want to study these things, what are the challenges we're going to have to overcome? The first is that these are very small. I already showed you mine are around 100 nanometers. That can be hard to image. They are also the changes that happen to these skyrmions, if you're moving them or destroying them and then reforming them, those changes happen very quickly. In general, magnetic field interactions are very weak, so they can be very hard to measure. And this is a purely magnetic field-based phenomena. And finally, we're trying to measure a vector quantity, the magnetic field. It has a magnitude and a direction at every point in space. And I've already said that these structures are three-dimensional, right? So we're trying to measure a 3D quantity over 3D space. And that is, in general, difficult. So, yeah, you have a question? Mm-hmm. So it's the reason that changes happen quickly is when I talk about changes, I'm talking about the fundamental timescale at which things change. And that has to do with how fast magnetic information can propagate. So if I take one magnetic moment and I twist it a little bit, how long does it take for this one to respond? And that's kind of a characteristic timescale. And that is what makes these interactions very fast. So sort of high level answer. So how can we overcome these challenges? Obviously, based on the title of my talk, it's going to be something that I know about, which is ultrafast and ultraviolet light. A little bit of a caveat to that. What I actually mean is extreme ultraviolet and X-ray light. And I'll talk about exactly what that means. And in order to do so, I need to talk about these two different types of light sources that I use. One of them is called high harmonic generation, and the other is from a synchrotron source. And I'm not going to get too much into details of how these work, but what you need to understand is that these are two different light sources that I'm using that provide light in the extreme ultraviolet and X-ray parts of the spectrum. Just to warn you about some acronyms that I'm going to use. Extreme ultraviolet, I've already said that one a few times. That is ultraviolet, slightly shorter wavelength, higher energy, you get to extreme ultraviolet. I'm going to have EUV up on my slides. That's what that means. If you go even higher energy, shorter wavelength, you get to soft X-ray, which is abbreviated as SXR. And beyond that, we have X-rays. The last acronym that I'm going to use is HHG, which stands for high harmonic generation. This is one of the lasers one of the types of light sources that we use to generate EUV wavelengths. So if any of these acronyms fade in your memory, just raise your hand and I will be happy to go over them again. So how do these tools help us solve the challenges of imaging skyrmions? Remember, our first challenge was looking at small things. So I want you to turn back to your neighbor and discuss, if you had the best optical microscope in the world, that means with visible wavelengths, what is the smallest thing that you think you could see if you had infinite budget, perfect lenses? Go. Would anybody like to share any ideas? What could you see, or what couldn't you see if you talked about that? Yeah.
Yeah, I guess in the field of microbiology, like optical microscopes can't really photograph or tell bacteria or like pollen. and they have use electron microscopes for that. So probably something like this.
Something bigger than bacteria or pollen. Do you have a guess of how big those are? Do you know? I don't know off the top of my head.
Or 3 to 5 microns.
3 to 5 microns. Okay. Yeah. So for, if, in case anyone didn't hear, they were saying somewhere in the realm of around 400 microns, which is around the minimum wavelength of, sorry, nanometers.
Yeah.
Thank you. Around the minimum wavelength of visible light. And that's actually correct. It turns out that there's a fundamental limit on how good your resolution can be that is tied to the wavelength of the imaging material you're using. So if you were to ask the question, for example, can you see atoms with an optical microscope? The answer is no, atoms are much smaller than 400 nanometers. Here's our electromagnetic spectrum. We have higher energy and smaller wavelength to the left. Atoms are around here, and visible light is all the way up here. An electron microscope, which is what we typically use if we want to look at individual atoms, is all the way down there. Skyrmions are around here. Kind of depends on exactly what you're looking at, but these are approximate positions. And the EUV and SXR sources are here. So we can actually, we could not achieve it with visible light, but we can achieve imaging of enough resolution to see individual skyrmions using these light sources. So that's our first challenge. The next challenge is looking at very fast things. So what do we usually use to take a picture of a fast moving thing? Does anyone want to take a guess? High shutter speed. That's exactly right. So someone asked me, what does ultrafast mean? And ultrafast does not mean that we're moving faster than the speed of light. It actually means we have an extremely fast shutter speed. So if we have a laser that is putting out individual pulses instead of a continuous stream of light, the length of those pulses is a pretty good analogy to the shutter speed on your camera. So our high harmonic generation based lasers can achieve pulses that last only a few femtoseconds. Femto is 10 to the minus 15th. So if I had a 10 femtosecond pulse, that would be a few quadrillionths of a second. And that means that it takes a few quadrillionths of a second for the front of the pulse, between the front of the pulse passing the finish line and the back of the pulse passing the finish line. If you picture this zooming around the lab, it's a little tiny pancake of light, about 100th of a millimeter going around. And that is our fast shutter speed camera. And with that, we can capture very fast motion. Any questions about that before we move on? Yeah.
We just have a picture of the scale, so the waves only oscillate like 10 or so times before the pulse stops.
It depends. I'm trying to remember where I got this picture from. The limit on how short a pulse can be is some fraction of the actual wavelength of that pulse. So in theory, you could have, they're called like single cycle pulses. But I have not done the math on whether or not this is an accurate number of cycles per pulse. But you could do that math, right? If we're looking for a wavelength of around, say, 50 nanometers, and our pulse is, say, 10 femtoseconds, you could do the math to figure out how many cycles are in that pulse. So our next challenge was weak magnetic interactions. On a very, very broad level, these experiments are just shooting a laser at our magnetic sample, and then whatever changes about that laser had to have come from our magnetic sample. And we need to be able to measure this magnetic information in order to detect a magnetic signal. And the bad news is that that interaction that causes a change in your beam path is generally very weak. But we can use this feature of the magnetic elements that exist in our magnetic sample. You might already know that electrons in any atom can only absorb and emit light at certain particular energies that correspond to some jump between energy levels in that atom. Those are just particular amounts of energy that can be absorbed or emitted. And if we have light interacting with matter, then those interactions are stronger at those energies because that's where the atom can see the light. So if we call those energies resonances, then we want to be working at a resonance of our magnetic elements. And it just so happens that magnetic elements such as iron, nickel, cobalt have these resonances in the region that we can reach with our two different kinds of EUV and SXR sources. So this is the right wavelength range to use if we want to look at a magnetic phenomenon. Moving on to our final challenge. This was how to get 3D information. If you're shooting your laser at some 3D object and the light can't get beyond the surface, then you're going to have no idea what's going on inside that material. However, if you can get transmission all the way through the sample, then you can somehow get information about the interior. It can be a little bit tricky to figure out what information came from the surface versus the bulk versus the back half of the sample, but it can be done. There's 3D imaging techniques that allow us to extrapolate the information about the inside of the material. But your sample needs to be at least somewhat transparent to the wavelength of light you're using. EUV and SXR wavelengths can penetrate long distances through the magnetic elements that we use to create skyrmions. So again, it's a good choice for imaging. So just to go over the challenges that we had and how our two light sources help us solve them. We had skyrmions are very small, and both of our sources have wavelengths small enough to resolve them. The HHG source is the only one that has this ultra-fast capability, but it does it very well, so we can get time-resolved information about our skyrmions. Both of these sources can reach these magnetic resonances, which enhance the magnetic signal. And finally, we can get three-dimensional information about our sample. So all of our problems are solved, right? I should have 1 billion papers by now. No, there are challenges to working with these wavelengths that make these experiments difficult. The first is that I said that these light can travel through magnetic materials. Well, they can't travel through air. So we have to work in a vacuum, and that is its own kind of challenge. They also can't travel through glass, which means we can't use focusing lenses to take images. Our perfect microscope with the infinite budget and the best lens, that's off the table because our light won't go through any glass. So instead of using lenses, we essentially replace all of our lenses with computer algorithms. And we do what's called computational imaging. You take a bunch of data and put that through data processing algorithms in order to reconstruct your image. Finally, these sources are not what's called turnkey, like you just press a button and the beam comes out. It takes quite a lot of expertise to work with them, both the HHG sources and the synchrotron. So that means there's a lot of attention that goes into every experiment. But that's good news for me because that means that I get to use my skills to do cool experiments. So with those challenges described, I want to give you a sense of exactly what experiments am I doing on these materials. Before I talk about this, are there any questions about the challenges of either the skyrmions or the UV light? Yeah.
Which source makes faster pulses?
Only the HHG source makes ultrafast pulses. I think yeah.
So you mentioned that it can't be conducted where there's air. Do X-ray machines have the same sort of problem, or is that, because those are also things that image 3D materials?
Yeah, so I think there you have even higher energy, shorter wavelength, where it goes back around to being transparent to air, I believe.
Yeah, you said the resolution of optical microscopes depending on its wavelength. Why not do some?
Why not use, right, so, I mean, part of the reason why we are using these shorter wavelengths is so that we can get that higher resolution. The reason why that's not ubiquitous and used everywhere is because of challenges like this. Optical sources of light are very easy to access, but as soon as you go higher energy, it becomes more and more difficult. Yeah. Mm-hmm. Yeah.
So I'm just wondering if like the size of the check marks, for example, it's the agent like worse than the synchrotron.
Yeah, so I put check marks in both because the question was, do the check marks say that this source is worse than this source in this particular category? It's not that it's worse, it's just that it can't reach the same level of resolution. So you might choose one over the other for a particular experiment, and I'm about to explain why I use one for one experiment and the other for the other experiment. They both have high enough resolution to image skyrmions, but one can get higher resolution. Yeah?
How high of a vacuum?
How high of a vacuum? So for this, I work in just high vacuum, which is like 10 to the minus 5 torr, roughly. We are not as concerned with surface cleanliness, which is when you typically need a much stronger vacuum. This is mostly just for transmitting the UV beam. So, oh yeah, one more question.
If each pulse has several wavelengths in it, does that mean that each pulse is like several different opening and closing to the shutter?
No, so the way that these wavelengths work, there's no mechanical shutter creating the pulse. It's actually it's called mode locking, where you add up a bunch of different frequencies in such a way that they create a single pulse. If you've thought about how like if you add up several different sine waves, you can either add them to create nothing or constructive interference. All the constructive interference is happening in one place to create a pulse. And that's how we have a pulse that's able to operate that fast, because there's no mechanical shutter that can move at femtosecond speeds. To talk about the two different experiments that I do. So one of them is 3D imaging of skyrmions. For this, I want that high resolution. So I'm working on the synchrotron source. And then I also try to make time-resolved movies of how these skyrmions destroy and reform. And for that, I'm working on the HHG experiments. So I'm just going to give you a really brief kind of general idea of what it looks like when I work on these experiments. So for the 3D imaging, we performed this experiment at the synchrotron at Lawrence Berkeley National Lab. We controlled the beamline remotely. This is what the software looks like. And that was 5 days, 24 hours a day of data collection. We were like doing shifts around the clock to get this data. And you need an enormous amount of data to be able to do computational imaging. After that, there is an enormous amount of data processing. And that has been going on for more than a year. I log into the supercomputer here at Jilla and try to turn information that really doesn't look like anything into what will eventually be a 3D map of this sample and the magnetic field at every point. On the other side, where I'm trying to make movies of skyrmions, I work in the lab. This is what my laser setup kind of looks like. And I'm working with the HHG source. And essentially, I am looking at my skyrmions, applying some kind of impulse to destroy them, and then watching them become destroyed and come back. And this is a lot of laser alignment, a lot of troubleshooting. But we get to see these very cool patterns of skyrmions. To talk about, yeah?
Are the visual representations necessary for your analysis, or like what do you get from visual representation that you can't get from, I don't know, just interpreting data in a non-graphical way?
Are you talking about this part or?
Yeah, we're talking about creating images out of data. Like,
Yeah,
why is the image necessary? What do you get?
that's a very good question. So in order to see the raw data, I wish I had a picture of the raw data here, but it looks like nothing. And each individual frame of the raw data has only a tiny fraction of the information that will be contained in this image. It wouldn't need to be an image. Like, we don't need to use a fancy visualization program to see the magnetic field in a way that we can observe. But the information that you get from that data processing will tell you what is the magnetic field at every point, and you can learn things about how the skyrmion shape is formed on a very micro level. So essentially, we do need to find that image. And most other techniques for imaging skyrmions look kind of like this. It's a two-dimensional representation. That three-dimensional representation allows us to compare what the skyrmions look like to those like very abstract rainbow hedgehog balls that I showed you at the beginning of the presentation. Does that answer your question? Awesome. So a day in the life of me as a researcher, I have these two different projects. One of them is very computational. I'd say 97% of the time has been spent on just analyzing the data. And even though 5 days of data taking sounds like a lot, very small in comparison to the huge amount of time spent analyzing that data. On the other side, with the experimental question, I spend about 30% of the time setting up the experiment, and then it was a little hard to read, but 60% of the time fixing laser issues. And that is maybe even an underestimate, depending on what kind of a week I'm having. And I haven't actually gotten into the data processing step for this experiment, so this is kind of a guess of how much time it's going to take me. And it is challenging to balance between these two different kinds of experiments, but it is nice to be able to, if my laser is not working and it's in the shop, I can log onto the supercomputer and work on my data processing. So in the next part of the talk, I'm going to just talk about a little bit about my journey in physics. So you get a sense of how one might become a graduate student, such as myself. So I did not have a good time with physics in high school. It was very hard to understand and to do. So if that's you, you're not alone. And I went to Williams College, which is a very small school, had a tiny department. And I kind of accidentally ended up in physics classes, but I loved them. My professors were great and my classmates were great. And there's also a good opportunity to get into research. I kind of very opportunistically applied to the group that I thought I would have the best shot of getting into, and I did. And I ended up working in that group for 3 years. And I thought when I was applying to grad school that this would be a bad thing, that I hadn't had enough variety of experience. But as it turned out, for working on the same project for 3 years, that experience is actually a lot more like grad school than working on lots of different projects for a few months at a time. Not to say, I think either way that you do it is good, but if you feel like you haven't had enough variety, there may actually be some strengths to that. And I had a fantastic time. There are a few organizations / activities that really helped me through physics in undergrad. We had a group called Women and Gender Minorities in Physics and Astronomy, or Ultrafast, which was just a great group of peers and mentors and allies. We didn't do very much like workshopping, but it was a good place to hang out, and that really helped me through my physics education. We went to the Conference for Undergraduate Women in Physics every year, which is a great resource. It occurs in January every year, and it kind of gives students a chance to share some of their research and get a sense of what grad school or future career prospects might be. There's also the Society of Physics Students. We did some watermelon activities and had a great time. It's just really nice to be in a community of physicists. I believe that the CU SPS meets here on Wednesdays. I'm getting some nods. Awesome. So I highly recommend checking that out. It is great to be friends with your fellow physicists. I think physicists are great, and it makes your research life much happier. I was also a teaching assistant, which I think is the equivalent of a learning assistant here at CU. And I really enjoyed that. That was really valuable to both to help me learn the material better and also to feel like I was connecting to the department in ways other than just like making myself better at physics. I was contributing to the environment. And now at CU, you can see I have a lot fewer pictures since the pandemic started just after I got to CU. I do the Women and Gender Minorities in Physics group. I also helped with PISEC, which is Partnerships for Informal Science Education in the Community. We kind of go around to local elementary schools to help students develop a identity of themselves as scientists. That's super fun. I'm involved with the United Campus Workers and CU Prime, of course. And this is both like a list of resources, but also generally advice. Get involved in both things that are not physics to keep yourself sane, but also things that contribute to your community, because it's very fulfilling and will make you a better researcher in the long term. And with that, thank you all for coming to my talk, and I will take lots of questions. There's a feedback thing as well.
Like Iona said, there's a feedback form that we have. So if you guys want to scan in that QR code or put that link in to your phone, we'd welcome that. And yeah, I guess we have plenty of time for questions. So what questions do we have for Iona?
I could go back to any slides. Yeah.
You mentioned they're stable for hours to days. This is proposed as a means of data storage. Are there ideas as to how to store data beyond hours of days?
That's a good question. I think, oh yeah, sorry, I'll repeat the question. The question was, is there a way to extend the stability beyond the time frame of hours to days? If something is stable in the lab for a matter of days, then that essentially means it's stable for a lot longer than that. We just haven't gone to the efforts to try to stabilize it. And the things, so my skyrmions, they have survived trips in the mail, many, many days. They've survived lots of experiments. The things that cause them to be destroyed are being near a magnet that in a way that destroys the skyrmion, or being heated up too much. So these are the kinds of things that happen a lot in a research lab, but if someone was developing this for a technological application, would be pretty easy to address. Yeah.
How do you make skyrmions? What's the process like with the magnets?
Great question. So I'm not, I wish I was an expert in this exact process, but it's something that we have materials scientist collaborators who do. But essentially, you would have, I'm going to go back to the relevant slide. Wow, it's a long way. If you have your magnetic field, then they apply a sequence of external magnetic fields in this direction, and then in this direction, and then this direction, getting weaker and weaker as they go. And they've done theoretical simulations. There's these programs that allow you to do what's called micromagnetics simulations that basically build in the physics of the interaction between one magnetic moment and another. And they've worked out what field sequence to do to cause these skyrmions to form. It is not an energetically favorable process for them to form, if that phrasing makes sense. But once they have formed, they don't want to unravel. But hopefully that's enough of an answer. Yeah.
So what exactly makes this in skyrmions? Like, how could they improve current storage like techniques? What about them makes them like a potential upgrade in the future?
That's a good question. I think someone tried to give me a lecture on why they're not an improvement, which is that magnetic materials are difficult to work with. But I think that magnetic transport can be very efficient. There's like low amounts of energy lost in heat or heat dissipation. This fact of being stable at room temperatures and without any kind of maintaining field is very good. Like if you think about, there's a search for room temperature superconductors, right? And skyrmions are not as well understood as superconducting technology, but we really want things that can function at room temperature anytime we're trying to make the technology for application. So that's one reason. But there's a lot of unknowns there as well.
Sai, you said that fermions are stable in the absence of this kind of magnetic fields. I guess maybe this is some like problem with magnets, but like you still do experiments under the influence of Earth's magnetism.
So the question was, does Earth's magnetic field influence anything? And in general, it doesn't. It's not strong enough to change the dynamics of the skyrmions. And to be clear, when I say its presence, it's stable in the absence of an external magnetic field. Kind of the reason I wrote that is that there are many kinds of skyrmions that actually do need an external magnetic field to exist. The ones that I work with do not, but people are also interested in, you need to apply a 200 millitesla field in this direction in order for these skyrmions to be stable. But that's already much stronger than the Earth's magnetic field. Yeah.
Based off the way these seem to be formed and their application, are there any applications of this, whether making it easier or new kinds of skyrmions that you could get if it was in, say, microgravity or made on the moon, or made without the influence of the Earth system?
So the question was, is there any research onto making, if it might be easier to make skyrmions on the moon or in microgravity or somehow divorced from the Earth's influence? That's a great question. I don't think there is. I don't know for sure. I don't think that gravitational forces have any particular impact on them. And in general, magnetic fields of like any device in this room, I said my skyrmions get just destroyed if they're near a magnet. If the magnet's on the other side of the room, they're fine. The field is not strong enough to destroy it. But I love the idea of skyrmions in space. Yeah.
So I've got two questions. The first being, you said that's separate and distinct states. Is it like discrete states or is it continuous states? Like, can you end up with a state that
Good question. The question was, are they discrete states or continuous states? And I believe in most cases, they're discrete states. That's kind of a feature of this topological protection, right? If I twist the ladder, I can either twist it this way or I can twist it that way. And if I don't twist it a full twist, then it's not a skyrmion.
Why can UV light not go through air?
So, you know how I was talking about, oh, the question was, why can UV light not go through air? I don't really need to go to a slide for this. There we go. I was talking about resonances and interaction between light and matter. EUV light does interact with the molecules in the air. So it gets absorbed and scattered and doesn't propagate through. Yeah? I'll ask someone who already did know a question already.
So you mentioned research and stuff like space movements. How do you decide any complication that we have to this?
You mean this slide?
Yeah.
Yeah, so the question was, how do you know if any of these are stable? So these are kind of mathematical objects, and I'm gonna have a hard time explaining how that like full twist idea corresponds to these other types of skyrmions, but maybe one of these. Okay, so the biskyrmion, or the hopthion. If you had two twists, for example, that would be stable. I don't know if I can describe how that the math works, but there's I think it would be called topological analysis to figure out whether or not you have created the equivalent of a twist, or if you've only done like a quarter of a twist and it's not stable. Yeah.
So during how was
You're asking how do I manage time between these experiments?
As an undergrad.
Oh, as an undergrad between the different activities.
No, I think you said you worked in the lab for 3 years.
Yes.
Yes, how did you manage that?
How did I manage working in the lab for 3 years with other school stuff? Yeah, so when I was working in this lab for the first 2 summers, I was doing like summer research. So I was in a summer research program and doing research every day during the summer. So I didn't have to worry about balancing that with schoolwork. Oh, and I should also mention that the institution I was at did not have any graduate students. So I was the senior student in that lab. In my senior year, I did a thesis, which meant that I was doing research as a class during the semester after a full summer of research. And I did find that challenging to manage the time, because when you have classes, you have problem sets, there's always fixed deadlines, and that always is easy to put ahead of the kind of more abstract deadlines of research. And that was one of the things that motivated me to want to go to graduate school, because I was very interested in the research and I wanted to be able to spend all of my time on it. I have since learned that that problem of time management doesn't really go away. I had 2 years of classes at grad school and still had to manage classes and experiments. And now that I'm doing all experiments, I have to manage one experiment versus the other. But I hope that I've gotten better at it. Does that answer your question?
How many hours do you have to work? Like,
Oh, how, so the stated time commitment for the thesis project when I was doing research while taking classes in undergrad was 10 hours a week. I think I mostly did that, except for sometimes when I was not able to give that much time, and then times when I was struggling to catch up, and I probably worked a lot more than that. But if each of my classes was supposed to be 10 hours a week, I was definitely working way more than that. I was working all the time. I would say I have a better work-life balance now than I did in most of my time in undergrad. Is there a question over here? Yeah.
Yeah, so you did mention that you can basically like destroy a skyrmion and then watch it reform. How exactly, like, what would you apply to a skyrmion in order to destroy it?
That's a great question. Because I said that they could be destroyed and not come back, right? So there is a trick to perturbing them enough that the pattern mostly disappears, but that it comes back. The main way that I would get skyrmions to go away, go to the slide, is by heating. So I actually hit it with another laser, not the EUV laser, but actually an infrared laser. And that laser is also pulsed. If I want to measure the dynamics, I need to have a very short initiation step, as well as a very short shutter speed. And that heat causes can I go back to my analogy of the ladder? Stretches out the ropes of the ladder so that there's more motion in between the adjacent magnetic moments. And the skyrmions kind of, if you think of these spots as representing the skyrmions, they kind of would spread out and begin to disappear and then come back, provided we don't heat it up too much that all of the magnetic information is lost. That answer your question? Awesome.
We described the skyrmions, or at least the mathematical objects.
Yeah.
Do you mean that in the sense that like the computer can kind of like algorithmically analyze it, like simulate like what they look like, or are you talking about like actual equations being put to describe the behavior of skyrmions?
It's more the former. The question was like, what does it mean to describe skyrmions as mathematical objects? Most of the work that has been done with skyrmions has been theoretical. They were theoretical long before they were actually realized in experiments. And essentially people were saying like, okay, we know that two magnetic spins want to align. What if we put a twist in it? What if we put two twists in it? What if we put a twist surrounded by another twist? And one way of defining that like mathematical object is you could define a three-dimensional magnetic field, and you could write a program that says, okay, start at one arrow and make every arrow point parallel to it until you either have everything parallel or you have one that's facing the other direction. That would be maybe a better answer to your question, which was like, how do you know if your configuration is stable? You could run that algorithm and that would tell you whether some random connection of spins was a skyrmion or not.
Yeah, so is it that each of the magnetic moments are like keeping each other in a stable state, or is there like something else keeping stable as a skyrmion?
The question was, is it that each of the magnetic moments are keeping each other stable? And the answer is essentially yes. Like, I'm not gonna keep trying to run through the slides. There's too many unless I have to. Because of the ropes holding the magnetic moments together, they can't unwind because it would require this to happen, which just can't happen. It can happen, but it's much better for it to have this very small disconnect than to do a full flip.
So like the shape of the material itself actually.
Yes, so the question was, can the shape of the material determine what a skyrmion looks like? It actually can. In this case, the shape of the material is just a flat layer like a cake. but we've made skyrmion-like objects that are defined because you have a little shell of magnetic material, and you can get the magnetic field in that shell pointing out everywhere like a hedgehog, and that would be a skyrmion-like object. It has that full twist. So that's a really great question. That the shape of your material can also influence the skyrmions. Yes.
To go back to the mathematical representations, is part of what you're doing just verifying the mathematical models and experimentation?
Yeah, so the question was, am I just verifying these mathematical models in the experimentation? Essentially, yes, since most of this representation has been simulations. But the thing that makes me excited about particularly this 3D imaging is that the majority of most of our conformations of skyrmions are entirely two-dimensional. Someone does a simulation, they say, I've applied this field sequence, I know that this sample should have skyrmions, I took a 2D image, and that 2D image is consistent with the existence of skyrmions, but they're not actually seeing the skyrmions. With this 3D imaging technique, we can actually see the skyrmions, and we can see, we could go down to like the 5 nanometer level of what one spin is doing to another. So that level of confirmation of a simulation hasn't really been done. Yeah. Oh.
You've, I remember you said that like the skyrmion image you've been working on for like over a year at this point. Is there any estimate on like when it'll be done? Like how long it's gonna take?
You sound like my advisor. The question was, is there an estimate of when this will be done? We're getting close. We're getting really close. I showed my lab mates today a better representation. It depends on how much time. That's not 1 year of like all day, every day working on it. This is like one of many projects. But I would say we are most of the way there. I hope.
Nice. Well, this is a great discussion we're having. I think you guys have awesome questions. If you do have more questions, then are you free to stick around for a little bit? You can come up and talk to Iona personally. So not next week, but in 2 weeks, we'll have our next talk from Pablo. He's going to be telling us about quantum circuits. So feel free to stop by then. We'll have more pizza and more science. In the meantime, let's thank Iona one more time.